Okay, in this video we're going to talk about second order linear constant coefficient homogeneous differential equations. So first of all, let's talk about linear second order differential equations with constant coefficients. Those are going to have the form ay double prime plus by, oh this is too thin. Okay, let's try this. Ay double prime plus by prime plus cy equals f of t. So here y is a function of t, and f of t is some function of t, and you're solving for y, and a, b, and c are constants, and a is not zero. So this is the general form of a linear, second order constant coefficient differential equation. Constant coefficients because a, b, and c are constants. And we'll talk about how to solve this for particular functions f of t. But for now, we will focus on the case when f of t is zero. So we will focus on the case when f of t is the zero function. And typically the notation is this f of t with these three, it's like an equal sign except with 3 bars. And that means, if you haven't seen it before, that f of t is just the constant function 0. If you just write f of t equals 0 with an equal sign, then that could be ambiguous because it might mean that f of t is 0 for some values of t, but not necessarily all of them. This is saying that f of t is 0 for all values of t. So it really is the constant function 0. It's not a function that has roots. Okay, it's not like it's sometimes 0. It's always 0. That's what we mean. So when we have that this function on the right is just 0, okay, we just write 0. But it's really the constant function 0 when we have the 0 here, right? Like the 0 that I just wrote, it doesn't mean the number 0, it means the function 0. Because if you think about what this thing on the left is, right? If y is a function, then the thing on the left is a function, and so the thing on the right has to be a function in order for them to be equal. So this is saying that we're looking for the y's that make the left-hand side the 0 function. That's the question. Okay. So when we have that differential equation, that's called a homogeneous differential equation. Okay. So what that means is I'll put a star or asterisk. It's ay double prime plus by prime plus cy equals 0. That's the equation we're going to solve. And strictly speaking, I mean, to be more clear, maybe it's better to put the 3 bars to say that it's the 0 function, but we usually just, the convention is just to write equals 0. Okay, so now there is actually a concrete answer to this, okay? There is a method for solving these equations, so that's what we're going to talk about. And then we'll talk about, maybe in future videos, we'll talk about where these differential equations show up. So to explain the general process, I have to introduce the definition. So the definition is, if you have two functions, y1 and y2, y1 of t and y2 of t, we say that they are linearly independent. This is a linear algebra term. Linearly independent on an interval I if neither of them is a constant multiple of the other. Otherwise, they are called the y1 and y2, those functions are said to be linearly dependent. So for example, if you have e to the 2t and e to the 3t, those functions are linearly independent, right? It's not like one is a multiple of the other. And another example is if you have e to the t and t e to the t. These are linearly independent. Now t e to the t is e to the t times t, but it's not a constant times e to the t, right? But if you had something like 2e to the t and 3e to the t, these are linearly dependent. Because how do you write 3e to the t as a constant times 2e to the t? It's 3 over 2 times 2e to the t, right? Okay, so basically there are functions that are in scalar multiples of each other. This definition extends to if you have more than 2 functions, like if you have 10 functions that are linearly independent. But okay, we're not going to go there in this video, and it's not just if neither is a constant multiple of another. It's a bit more complicated. If you're familiar with linear algebra, then you're familiar with this concept of linear combinations, and it's in that sense that we're talking about linear independence. But for this video, you just need to think about what happens when you have 2 functions. Also, don't worry so much about the interval I. I mean, when you have a differential equation, technically it just needs to happen on an interval, right? But for these videos, we're not really making a big deal out of that. Okay, so, I mean, mainly the interval we're talking about is just the entire real number line. Okay, so now that we have introduced linearly independent functions, we can state this theorem. So this is going back to the differential equations that we're trying to solve, the linear second order differential equations. Actually, for the theorem that we're about to state, they don't have to be constant coefficients. Your a, b, and c could be functions of t, but since we're just focusing on constant coefficients anyway, let's just only talk about that. So we're trying to solve the homogeneous differential equation. This is the one that will be the topic of this video, right? This one, not the one where f of t is not 0. Okay, this is the equation we're talking about, the one with the star. Okay, so the theorem applies to the equation with a star, and it says that if y1 and y2 are linearly independent solutions to that differential equation with the star, then the general solution to the starred equation is y equals c1 y1 plus c2 y2. Okay, that's what this theorem says, which we're not going to prove. I don't think the proof is that complicated, but this video is mainly about applying the theorem. So let's make sure we understand what this is saying. So it says that, so you have that differential equation with a star, right? And you're trying to figure out what all the solutions are. And the theorem says that if you have 2 of the solutions, if you have 2 solutions, y1 and y2, and neither of them are a multiple of the other, so they're in some sense like they really are like somehow genuinely different, right? It's not like you have, e to the t and then 6 e to the t and 7 e to the t. It's like a different, like it's a different function, sort of. It's not just a scalar multiple. You're not just taking a scalar multiple and producing more functions. You have two functions that really are somehow like different, right? They're linearly independent. That's what we mean. That they are not just gotten by scaling one function to get the other. So if you have these two linearly independent solutions, y1 and y2, then actually all of the solutions have the form a constant times y1 plus a constant times y2. So that's all of the solutions to the equation. So this is different than when you had the first order linear equation, because there you had one c, right? You had an arbitrary constant, but there was just one arbitrary constant. In this case, we have two arbitrary constants, c1 and c2. So there's still infinitely many solutions, but there's just going to be somehow more solutions in some sense, even though it's still an infinite number, because now you have like a whole plane's worth of solutions, right? Yeah. For each pair, C1 and C2 of real numbers, you get a solution, C1, Y1 plus C2, Y2. Okay, and what that means, we'll see that for the initial value problems for these differential equations, we actually need two initial conditions. We'll come to that. But, okay, so going back to this theorem, what this is saying is, right, this theorem is helpful because it's saying that, oh, well, once you have your y1 and y2, then you actually know the general solution. It's just this, right? So the theorem is saying that all you need to do is find the y1 and y2. So the theorem says that to solve the differential equation, and this is only referring to the homogeneous one, okay, you just need to find two linearly independent solutions, the y1 and y2, because once you have those, then you get all of the solutions. It's just c1 y1 plus c2 y2. So now, how do you find the y1 and y2? So how do you find these? The y1 and y2. Well, that's what we're going to talk about now. So you have this differential equation, ay double prime plus by prime plus cy equals 0. And it turns out that this is what you can do. So the first step is you form what's called the auxiliary equation. Or sometimes it's called the characteristic equation. The auxiliary equation is the equation ar squared plus br plus c equals 0. So basically what you're doing is you're replacing the y double prime with r squared. Right? You're changing that to that. You're changing the y prime to r, and you're changing the y to 1. Okay. So you get this equation. It's a quadratic, and now you find the roots of this. Using factoring or the quadratic formula. Either way, you're going to find the roots. And then, so the theorem says, here's the next theorem. The theorem basically just tells you how to find the y1 and y2. So when you find the roots of a quadratic equation and your a, b, and c are real numbers, there's three possibilities. The first, maybe I'll put it below. The first possibility is that you get two distinct real roots. So if you get two distinct real roots, R1 and R2, then y1 is e to the r1t and y2 is e to the r2t, these are two solutions to the equation. And of course, they're not, because R1 is not equal to R2, they're linearly independent solutions. I mean, I'm putting them in parentheses because, you know, it's pretty clear that one is not a scalar multiple of the other. So anyway, two linearly independent solutions to the starred equation. So that's case one. Case two is if you have a repeated root. So if you get a repeated root, okay, we'll do some examples of this so that you understand what this is saying. But basically, it's when you have something like, it's like if you have r squared plus 6r plus 9, okay? When you factor this, it's r plus 3 in parentheses squared, right? I mean, we would say that -3 is a repeated root. Or it's sometimes called a double root. It's repeated because you have an exponent which is greater than 1. So case one is if you had something like, r squared plus 5r plus 4, and that factors as r plus 1 times r plus 5, and then your roots are -1 and -5, right? So that's two distinct real roots. This case is a repeated root. The -3 is a double root, a repeated root. So in this case, if you get a repeated root, let's call it r, then your y1, you can take to be e to the rt, and y2 to be t e to the rt. These are linearly independent solutions. Notice that I don't have a subscript for the r for case 2 because I have just this one repeated root, right? So it's not like I have to call my roots different names, like r1 for one of the roots and then r2 for the other root. It's the same r. Okay, so that's case 2. And then case 3 is if you have complex roots, right? Because you can get complex roots. Now when you have a quadratic equation with real coefficients, and if you have two complex roots, then they turn out to be something called complex conjugates. So if you get two complex conjugate roots, alpha plus or minus I beta. So if you have a quadratic and one of the roots is alpha plus I beta, then the other root is the complex conjugate, which is alpha minus I beta. So if you get two complex conjugate roots, so let's just call them R1. It doesn't matter which one is R1 and which one's R2. You just call one of them R1, the other one's R2, okay? So let's say that R1 is alpha plus I beta and R2 is alpha minus I beta. Well, we actually won't use that in the, but these are the complex conjugate roots. Okay, then y1 is e to the alpha t cosine beta t, and y2 equals e to the alpha t sine beta t. So this is beta t is, you're doing cosine of beta t and sine of beta t. Okay. But typically you don't actually have the parentheses. That these y1 and y2 are linearly independent solutions. And again, it is important that they're linearly independent, but you can kind of see that they're going to be linearly independent. So it's not really part of the theorem. Okay? So those are the y1 and y2. This theorem tells you exactly what to do whenever you have this homogeneous equation. It literally tells you how to solve it. You first set up this equation, okay? You find the roots, which you know how to do, hopefully, and then you, depending on what kind of roots you get, if you have case 1 or case 2 or case 3, okay, they literally tell you what your y1 and y2 are, right? So in case 1, here's your y1 and y2. Case 2, here's your y1 and y2. Case 3, here's your y1 and y2. And so in all these cases, the general solution, right, the theorem says, the first theorem that we said, says that the general solution is c1y1 plus c2y2. Okay. So actually, the second theorem is not that hard to prove. You just plug in. Remember, to check whether these are solutions or not, you can just plug them in and check that they satisfy the equation. And it turns out that if you plug them all in, for the different cases, they will satisfy the equation. I'm going to leave out the details of this. I mean, if you look in the textbook, it will probably show all the algebra, but the important thing for this video is just to know that it's true. And we will talk later, though, about, how would anyone come up with, see, case two is somewhat complicated because of the t e to the rt. Case 1 is not that bad. I mean, if you have, I think it really is better if you did it. Okay, if you have two distinct roots, then checking that e to the r1t and e to the r2t are solutions to this. I mean, you can probably do this in your head. If you take the second derivative of that, you're going to get an r squared e to the rt. And then if you take the y prime, you're going to get r e to the rt. And if you plug in y, you get e to the rt. And basically what happens is you can factor out the e to the rt, and then you're going to get ar squared plus br plus c, and that's 0, because r is a root. Okay, but yeah. Okay, I'm not going to write out the details of that. The case 3 is probably the least obvious where this comes from, because you can check that it's true that if you, take the derivative of each of these things and plug them in, that they really do satisfy the equation, right? That your y satisfies this differential equation. But it's not easy to see how anyone would come up with this. And this has to do with complex numbers, right? Case 3 is the one with complex numbers. So we'll talk about the complex exponential, e to the I theta, and then we'll see where this comes from. But remember, for checking that something is a solution, you don't need to know where it comes from. You just need to know that when you plug them into the equation, that the equation is satisfied. All right, let's look at some examples of this. So part A says find the general solution of the differential equation y double prime plus 9y prime plus 18y equals 0. Okay, and then part B says find the unique solution that satisfies the initial conditions y of 0 is 5 and y prime of 0 is negative 21. Okay, very typical problem. So for part A, we set up the equation, right? R squared plus 9r plus 18. We set it, the equation is r squared plus 9r plus 18 equals 0. We need to solve for r. And if worst comes to worst, we have to use the quadratic formula, but can we factor this? Yes, we can. It's r plus 3 times r plus 6 equals 0. And so remember when you have two terms, right, you have r plus 3 and r plus 6, the product is 0, then one of these must be 0. So r plus 3 is 0. If you take away 3 from both sides, you get r is negative 3. For the second one, r plus 6 equals 0. You take away 6, you get r is negative 6. So your roots are distinct. They're negative 3 and negative 6. So you just call one of them negative 3 and the other one negative 6. So let's just say that r1 is negative 3 and r2 is negative 6. If you said that r1 is negative 6 and r2 is negative 3, that's perfectly fine. You're going to get the same answer. Anyway. So now this is case 1, right? And so if you don't remember, we look at the formula. Here's your y1 and y2. So we know that the general solution is c1 e to the negative 3t plus c2 times e to the negative 6t. And that's the answer to part A. Find the general solution. Okay, pretty simple, right? This is the easiest one if you have two distinct roots. So for part B, you have to find the unique solution that satisfies the initial conditions. So what we need to do is we need to find the C1 and C2, right? We need to find the C1 and C2, and then once we have the C1 and C2, then we plug those in, and then we get our function. Remember, this when we say for part A that this is the solution, we're saying that C1 and C2 can be any real numbers, right? Where C1 and C2 are any real numbers. So there's an infinite number of solutions to the differential equation. But when you have part B, right, the unique solution that satisfies these initial conditions, so now they tack on these two additional requirements that y of 0 has to be 5 and y prime of 0 has to be negative 21. And that's going to narrow down your C1 and C2 to only one possibility. So how do we figure out what the C1 and C2 are? Well, we plug in, right? We have the y, we plug in 0, and we're supposed to get 5. And we need to find what y prime is. What y prime is. So let's figure out what y prime is first. So y prime is, okay, you just take the derivative, negative 3 c1 e to the negative 3t minus 6 c2 e to the negative 6t, right? So now we have y and y prime, so then we plug in our initial values. We know that y of 0 is, what do you get when you plug in 0 into your y, into your t? When you plug in t equals 0, you're going to get c1, so I'm looking here, c1 times e to the 0. Well, that's c1. And then when I plug in t equals 0 in here, I'm going to get I'm going to get plus c2, right? So it's c1 plus c2. And then I do the same thing where I plug in 0 and for y prime, if I plug that in, I'm going to get negative 3 c1 minus 6 c2. And we're given that y of 0 has to be 5, so c1 plus c2 is 5. And we're given that y prime of 0 is negative 21. So negative 3 c1 minus 6 c2 is negative 21. Now we have to solve for c1 and c2. Okay, now you need to do a little algebra here. So I guess the first thing we could do is we can multiply the top equation by 3. So 3c1 plus 3c2 is 15. Negative 3c1 minus 6c2 is negative 21. If you add the two equations, you get 3c2 minus 6c2, negative 3c2 is negative 6, divide both sides by negative 3, c2 is 2. And then you plug in your c2 into, say, the first equation, because it's easier, and you get that c1 is equal to 3, right? c1 plus c2 is equal to 5, c1 plus 2 is 5, c1 is 3. So your c1 is 3 and your c2 is 2, therefore the answer is y of t equals 3 e to the negative 3t plus 2 e to the negative 6t. That's the function that satisfies the differential equation and also these initial conditions. Okay? Okay, let's do another one. Let's do the next example. Oops. Next example which is to find the general solution to y double prime minus 6y prime plus 85 over 4y equals 0. Okay, so that's part A. And let's use t as the independent variable. I think you should try doing this on your own and see what you get, and then we'll go over the answer. Okay, let's go over the answer. So we set up the equation r squared minus 6r plus 85 over 4. No, why don't I use a lighter? Okay, r squared minus 6r plus 85 over 4 r to 0. And this might be annoying to factor. I mean, you could multiply both sides by 4, but it's still not very easy to factor. So let's actually use the quadratic formula for this. So we get r is negative b plus or minus the square root of b squared, so that's 36 minus 4ac, all over 2a. And this is going to be 6 plus or minus the square root of 36 minus 85 all over 2. What is 36 minus 85? That is going to be, so you do 85 minus 36 and then multiply that by negative 1. So you're going to get the square root of 49. Is that right? Negative 49. All over 2. And square root of negative 49 is 7i. So you get 6 plus or minus 7i all over 2. And you want to break this up to get your alpha plus or minus I beta. You write this as 6 over 2 plus or minus 7i over 2. So then this is going to be 3 plus or minus 7 over 2i. So what's our alpha and what's our beta? Alpha is 3, right? That's our alpha. And our beta is 7 over 2. So we have case 3 now. Case 3. This one. If you get two complex conjugate roots, okay, then your y1 is e to the alpha t cosine beta t, y2 is e to the alpha t sine beta t. So in this case, okay, we have alpha is 3 and beta 7 over 2, and so our general solution is y equals c1 e to the alpha t cosine beta t, so that's this plus c2 e to the alpha t sine beta t. So that's part A. And then part B says find the unique solution that satisfies y of 0 is negative 5 and y prime of 0 is negative 22. Well, first of all, let's make it clear that this is the answer to part A. That's the answer to part A. And we basically, to do part B, you just do the same thing, except the derivative is going to be more complicated, right? So what do you get when you take the derivative of y prime? I mean, when you take the derivative of y. Well, you have to use, what rules do you have to use here? There's a product rule, right? Because there's e to the 3t, and then there's a cosine of 7 over 2t. And then for each of those, there's a chain rule, because, you know, you have a 3t and a 7 over 2t. Fortunately, it's not that complicated because you just pull the constant out, right, with the chain rule. So, C1, now you're taking the derivative of this, so when you pull the constant out of the derivative, you have C1 times the derivative of this product. So that's why you should put a big bracket like this, because you're going to get, do you see what you're going to get when you're doing the product rule? You're going to get something times something plus something times something. And you're going to get C1 being multiplied by that whole thing. So that's why, right, what you're going to get is something times something plus something times something, and then C1 is being multiplied by the whole thing, and that's why I put this bracket on the left. Okay, so what goes in the bracket? The derivative of e to the 3t times cosine 7 over 2t. And that's the first function times the derivative of the second function. So it's e to 3t times negative 7 over 2 sine of 7 over 2t. Because remember, the derivative of cosine is negative sine, right? And where does this 7 over 2 come from? It came from the chain rule because I had to take the derivative of 7 over 2t. Okay, so I have that plus cosine of 7 over 2t times the derivative of e to 3t, which is 3 e to the 3t. So I have that, and then plus c2, and then the derivative is e to the 3t times 7 over 2 cosine 7 over 2t plus 3 e to the 3t sine 7 over 2t. Okay. I'm just going to leave out the parentheses since we don't need them. Now at this point, we can plug in our y prime of 0. So we know that y prime of 0 is, so what do you get when you plug in 0 in? So you're going to get 0 here. You're going to get sine of 7 over 2 times 0. 7 over 2 times 0 is 0, right? So sine of 0, this whole thing is 0. So actually, this whole thing is going to be 0. And then you're just going to get, and similarly here, this whole thing is going to be 0 because you have a sine of 7 over 2t. And you're plugging in t equals 0, and sine of 0 is 0. So all you have left, when you plug in 0 here, you're going to get 3e to the 3t times cosine of 0. Cosine of 0 is 1, so you get 3e to the 0, which is 3. So I'm just going to be left with 3c1 for the first term, and then for the second term, when I plug in t equals 0 here, I'm going to get well, when I plug in t equals 0 here, I'm going to get 1 times 7 over 2 times 1. So I'm going to get 7 over 2. I'm going to get 7 over 2 c2. Let me double check. Yeah, I think that's right. And then when I plug in 0 in here, I'm going to get, again, this term is going to be 0 because I get a sine of 0. And then I'm just going to be left with C1 times e to the 0, which is 1, times cosine of 0, which is also 1. So I just have y of 0 is C1. So let's just write that down. So y of 0 is C1, y prime of 0 is 3C1 plus 7 over 2 C2. And we're given that y of 0 is negative 5, so C1 is negative 5, and then 3C1 plus 7 over 2 C2 is negative 22. That's what we're given in the problem. Well, this is actually really easy, right? Because we're actually given what C1 is. C1 is negative 5. So for the second equation, you get negative 15 plus 7 over 2. C2 is negative 22. Add 15 to both sides, you get 7 over 2. C2 is negative 7, so you get C2 is negative 2. And so we get the answer. The answer is y of t equals negative 5 e to the 3t times cosine of 7 over 2t minus 2 e to the 3t sine of 7 over 2t. Okay. So that's one where you had two complex roots. Let me see if I can find one where you have where you have a repeated root. Well, it's not that hard to make one up, but let's see if I can find one. Yeah, okay. So let's just do one more example. Let's say you wanted to find the general solution. This is part A. Find the general solution to y double prime minus 6y prime plus 9y equals 0. Well, this is really easy, right? You just set up the equation, r squared minus 6r plus 9 equals 0. We solve for r, you factor, so you r minus 3 in parentheses squared is 0. You solve for r, you get r is 3. So you get one root, it's a repeated root. And so, using case 2, we see that the solution is c1 e to the 3t plus c2 t e to the 3t. And that's it. That's the answer to part A. Now let's do part B. Of course, we have to, do something with more computation. So find the unique solution that satisfies the initial conditions. Y of 0 is 2.5 and y prime of 0 is 7. By the way, they don't have to give you y of 0 and y prime of 0. It could be y of 1 and y prime of 1 or something. It's just you need two equations to solve for the c1 and c2. And it's easier when your t is 0. You just get easier algebra. Okay, so first we have our y. Let's take the derivative to figure out y prime. So y prime is going to be 3c1 e to the 3t plus c2, and now I have a product rule. So I have t times the derivative of e to 3t, that's 3 e to the 3t, and then plus e to the 3t times the derivative of t, well, that's 1. So I get this. And if I wanted to, okay, you could factor out an e to the 3t here. But since we don't have to, let's not. Because we're just, at this point, we're just going to plug in t equals 0 in, right? Because of our initial conditions. So when you plug in y of 0, let's see. Y of 0 is C1. Oh, well, it's actually just C1. Because when you plug in t equals 0 here, right? When you plug in t equals 0, you're just going to get that this whole thing ends up being 0. So that makes the algebra easier. So y of 0 is C1, and y prime of 0 is, well, when you plug in t equals 0 here, that's going to be 0, that's going to be 1, and that's going to be 3C1. So you're going to get 3C1 plus C2. So you're going to get C1 is equal to 2.5 and 3C1 plus C2 equals 7. And this is easy because we're given C1 is 2.5. We plug into the second equation. C2 is 7 minus 3C1. That's 7 minus 3 times 2.5. 7 minus 7, let's see, 7 minus 7.5 is negative 0.5, which is negative a half, since I don't like fractions. So, and C1 is 5 over 2, because I don't like fractions. So the answer is y of t is C1, 5 over 2, e to the t, e to the 3t, plus C2 minus 1/2 t e to the 3t. Now we basically have done all the possible cases for the homogeneous second order linear equations with constant coefficients. So let's review what we did in this video. So we talked about the second order constant coefficient linear differential equation, right? Homogeneous. That's important. This video is only for homogeneous. It doesn't apply when the thing on the right is not 0. The theorem says that if you have two functions, y1 and y2, that are not scalar multiples of each other, then the general solution is just c1y1 plus c2y2. So once you have two independent solutions, you can get all of the solutions to the equation. So we just need our y1 and y2, and how do you find that? You set up the auxiliary equation, ar squared plus br plus c equals 0. You find the roots. If it's two distinct roots, it's that. If it's repeated root, you get a different thing. If it's complex conjugate roots, it's a different thing. And we did some examples of each of those cases. And so just general tips for doing these problems is, finding the general solution is easy, okay, for the most part. It might take some practice for the complex roots, because for the complex roots you have to use the quadratic formula. So where was that here? Right? So there might be, some simplification here that you have to be aware of. So like, let's say that you had, like let's say that you had 6 plus or minus 6i over 2, right? You just want to be careful and make sure that you do simplify this as 6 over 2 plus or minus 6 over 2i, and then write that as 3 plus or minus 3i, and not 3 plus or minus 6i or 6 plus or minus 3i or something like that, right? So just be careful with the simplification, and but in terms of the process, it's pretty straightforward. And then I guess one thing that you also want to make sure of is, so another somewhat common mistake is if you have, r plus 7 in parentheses squared equals 0, your r is negative 7, right? It's not positive 7. So just be careful about that. That's a common mistake with the algebra. But in terms of what to do, it's pretty straightforward, because the theorem basically tells you what your y1 and y2 are, and then if you get a problem which is an initial value problem, I think it's easier to, once you have your y, find the y prime and then plug in your 0 or your initial values into your y and y prime after you figure out what y prime is. So figure out what y prime is first and then plug things in after that. I think that's easier than plugging in your initial value for your y and then going back and taking the derivative of y and then plugging in the initial value for the y prime. Okay, I think it's just more organized. See, when you look at how I did these problems, once I figured out what y is, I found y prime, and then I plugged in the values. And I did that for the other examples. I think that just keeps things a bit more organized. Okay, so things we didn't talk about in this video is, first of all, so again, proving this theorem is not so hard, that these solutions work, because you just plug them in and see that they work. But one thing we haven't really talked about is how you would come up with these things, especially case 3. And that involves things with complex exponentials, which we'll talk about. And then one thing, of course, we haven't talked about is where would these second order differential equations show up in practice. And then another thing we haven't talked about is what happens when you have a non-homogeneous differential equation. So what happens when you just have a general f of t? And that's something we'll also talk about in future videos. Okay, thanks.